Okay, hey guys. Alright, I gotta try to be fast with this, so here goes. Looking at the try on your own problems that I told you to do, right away, you notice that number one is the same thing we already did. If we go back, see, same thing, cosine plus 1. So we could make it cosine minus 1. That's not really different enough. So here's this one. We'll do this. This will be fun. I made the directions a little more explicit. I want the general solution, and that's what we did in class. But there's also something else called the particular solution, which is all the solutions just on a certain interval. So again, I'm asking you to do that interval. That's just the first trip around the unit circle. So starting at 0, come all the way around to 2 pi, and just give me only those solutions that you come to in the first rotation. That's called the particular solution. But anyway, for this problem, I'm going to go ahead and do it two different ways again, I think. Hopefully the way that jumps out at you guys is to just divide by 2. And then you have sine squared of x equals a half. Then at this point you could take the square root of both sides, remembering that that generates a plus or minus. So you now have just sine of x equals plus or minus 1 over root 2, which, if you rationalize the denominator, gives you plus or minus root 2 over 2, which you should immediately recognize as a unit circle value. So if your brain's working, then you're looking and you're thinking that on the unit circle, the place where sine equals plus or minus root 2 over 2, those are y values. So positive root 2 over 2 is located here at 45 degrees. Also here at 45 degrees. Both of those are positive root 2's over 2. But we can also be negative root 2 over 2. So that would be 45 degrees down here in quadrant 3 and also in quadrant 4. So that means our complete solution set, this says theta, so this should say theta. My bad, these should all say theta, theta. So our solution set will be theta is equal to, now for the general solution, I want every single angle. So that's when we'd have to take the first one, let's say pi over 4, and then add to that the number of degrees that would rotate me onto the next one, next one, next one, next one. So those are 90-degree rotations. So that's pi over 2 times k, where k is an element of the set of integers. So that is the general solution. Now the particular solution would just literally be these 4 points that I plotted. So the particular solution would be theta equals, let's do it as a set. Theta is an element of the set that contains these 4 points, which are 1 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. That's it. Now I said I would do this 2 ways, so I will. Where am I? Here? You can't see my thing. Okay, sorry. So here we go. We're going to do the same problem a second way. So a different way that you might have done this problem is to recognize that you've got 2 sine squared. That's pretty darn close to one of our versions of the double angle identity for cosine. So again, over here, you hopefully remember that cosine of 2 theta is 1 minus 2 sine squared theta. These are supposed to be thetas, by the way. Theta, theta. So okay, then just subtract this from both sides. You would get 0 equals 1 minus 2 sine squared theta, which that whole thing now immediately turns into the cosine of 2 theta. And at this point we could do a u substitution. By the way, the u substitutions are completely unnecessary. I can talk in class tomorrow about that, but I guess I'll still do it for the moment. It's a nice little crutch, I suppose. But let's just call this cosine of u And then we can make our solution set for u. So it's asking when is cosine 0? Cosine is x. So we would get two positions here and here. And so that means u is equal to pi over 2 plus pi times k, where k is an element of the set of integers. And then this is when we remember that, hey, u is actually just 2 theta. So if you let u equal 2 theta and then you divide by 2, now we're dividing everything by 2 technically. So divide that by, the only thing that doesn't get divided by 2 is this little piece of text here. Technically the u will get divided 2. So u over 2 would be the same as theta, which would be the same as this. My kids are going nuts. I'm going to ignore them. So theta equals pi over 4, because I'm dividing by 2, plus pi over 2, k, where k is an element of the set of integers. So I don't know which of these methods felt easier to you, but you're noticing, I hope, that we're getting the exact same solution set. If it's not obvious, then plot those points. And pi over 4 would be the first one. Okay, I had to sneeze. I did it. So pi over 4 would be the first solution, and then every 90 degrees you'd get another. So we get another one here. We get another one here. We get another one here. And you can see that, yeah, that's the same solution set we had the first time. Remember, this thing that we graphed, this is a graph of the solution set for u, right? Meaning that's the solution set for 2 theta. That's not really what we want. What you see down here is the solution set representing all the solutions for theta. That's why you're seeing two different things. But anyway, there you go. Oh, I forgot. Again, this is my general solution. So my particular solution would again just be these 4 answers only. We would say theta is an element of the set that contains these 4 things. My dog. Pi over 4. 3 pi over 4. 5 pi over 4. And 7 pi over 4. Oh my lord. Could you all hear that? Those screams are blood curdling. So I'm going to have to go deal with that. I'll be back. Okay, I'm back. And why is that being weird? Okay, there's the particular solution. It'd be those 4 values. And I don't have a heck of a lot of time left since my family had a meltdown. So I'm going to do one more for you guys. Maybe that's it. Looking at 2. That's pretty similar to the one from yesterday. This might be the most interesting one. I was going to give you guys a bonus one, but I'm definitely cutting that. I'm going to do 3. Then I got to go. Sorry, but I do. But y'all can talk to me about the other ones tomorrow. I'm not leaving you in too big of a lurch, so sorry. But looking at number 3, this one here, I'm hoping that you recognize that, kill this 3, I hate this 3. This is our equation. We really don't ever want to have more than one trigonometric function per equation. So if I could turn this sine into cosine, that would be a good idea, but I can't. If I could turn this cosine into a sine function, that would be a good idea. And I can use a Pythagorean identity. Remember, if sine squared plus cosine squared equals 1, then you can subtract cosine, no, super psych. You subtract sine squared. And then cosine squared will be 1 minus sine squared. So we're going to make that substitution right away. So we'll have 3 times 1 minus sine squared theta. That'll be minus sine of theta, and it'll equal 1. Next, we'll distribute the 3, so we'll have 3 minus 3 sine squared theta minus sine theta equals 1. And roundabout now, I'm hoping you're noticing that you've got a sine squared and a sine and a constant. This should be feeling a lot like a quadratic to you. And ax squared plus bx plus c, which we would try to make equal 0 so we could factor. So that's what we'll do. Since I've got a negative on my sine squared, I'll just kick everything over to the right hand side. So this side is going to all go down to 0. And over on the other side, I'll have a positive 3 sine squared from adding it to both sides. I'll add a sine to both sides, so I'll get a positive sine over here. Then if I subtract 3 from both sides, then I'll have a minus 2. And so here's my equation. At this point, you could do a let statement if you wanted to. We could replace all the signs with u's. It's not necessary, but it still might be something that makes you feel more comfortable as you're doing this problem. So if I replace this with u's, then maybe you can sort of better see that to factor this, we'll have a 3u and a u. 3 times negative 2 is negative 6, so we need factors of negative 6 that add up to positive 1, so it's actually going to be the 3 and the 2 themselves. I've already got a 3, so to get a factor of 3 I only need a 1 here. That's the trick for the outers and inners. For the inners I need a 2, and to get a positive u I'm going to want the 3 times 1 to be positive, and to bring the 3u down to a 1u I want the 2u to be negative. Just trust me on this. That's the correct factored form. Again, you can FOIL it from here to make sure it's right. But there you go. At this point we would use the zero product property to break this apart. We'll take the first factor, the 3u minus 2, we'll set it equal to 0, and that'll generate some solutions for us. Then over here we'll take the u plus 1, set that equal to 0, that'll generate more solutions for us. And over here, if I add 2, divide by 3, I get 2/3. Over here, if I subtract 1, I get u equals negative 1. Now is the part where we remember that u actually represents sine of theta. So here we're saying the sine of theta is 2/3. And here we have the first sort of instance where this is not actually a unit circle value. So to solve for theta, we'd have to just use inverse sine. And so you won't actually be able to give me like a real answer. Like in radians, you'll just have to tell me that the angle is the inverse sine of 2/3, whatever the hell that is. But that would be it. That would be your answer. Over here, if sine of theta is negative 1, well, we can do that. Sine is our y value. Negative 1 would be down here. So here we know that theta would be 3 pi over 2. Okay, so that's all well and good. As far as my general solution, how do you write an expression that models every place where this could happen? Well, it's a sine, so basically you're thinking where on the unit circle do you get 2/3? Well, 2/3, if this is 1, 2/3 would literally be 2/3 of the way up the y-axis. So it's 2 positions again in these 2 quadrants. I don't know what it is. It looks like maybe it's, I don't know, more than 45, I'll say that at least. But it's those 2 positions. So, I don't know. I'm just not going to mess around with this, I don't think. I'm just going to say, if it's not unit circle values, then I won't ask you to write me a general expression. That gets a little weird. You could give me the particular expression, though. Actually, maybe even that you can't, because even then you'd still have to figure out who this guy over here is. And I don't feel like it. Okay, fine, we got to do it. Bugger all. All right. Fine. First of all, I got to move everything up. Buy a little more room. All right, here's the deal. If this angle right here is theta, then that angle right there, that's the inverse sine of 2/3. So who's this angle over here? Wouldn't it be 180 minus whatever theta is? And if you don't get that, too bad, I'm not explaining it. But one of our answers will be the inverse sine of 2/3. Then the next answer right here will be 180 minus the inverse sine of 2/3. Or if we're staying in radians, then it's pi minus the inverse sine of 2/3. And then of course our third answer is the one down here, the 3 pi over 2. So if we're answering part B, the one where you just give the particular solution, only the solutions from this interval, then it would be these three values here. So we should say theta is an element of the set that contains these three things. That's it. Gotta go. Talk to you tomorrow. Oh crap, my face is in the way again. Oh crap, I don't know how to move my face. Move face. Bring face back. Okay, there you go. Those are the answers. Inverse sine of 2/3, pi minus inverse sine of 2/3, and 3 pi over 2. So that's a little different, but hopefully you can handle it. Like I said, gotta go. Talk to you tomorrow. Bye.